Hi everyone, and this is Control System class. In the previous lecture class, we have learned about the type of response of transfer function. Today we are going to learn control system. If you can remember, the last time we have learned that transfer function give us a response and how many type of response can transfer function give and which parameter in transfer function can affect to response. Okay, the way we are going to learn control, we'll use block control because we cannot change transfer function. For example, the temperature control in air conditioner. Transfer function is the thing which represents system, which is air conditioner, and we cannot change anything about hardware. That is transfer function. So we have to use block control to control temperature. Today, we are going to learn PID control. And what is PID control? PID control is a compensate system which make response be in the same as input. And we usually use unit step as an input. So it means that we have to make response to look like input, which is unit step. Okay, next we're going to do a simulation. To introduce, you got to know more about PID control and how it works. First, open MATLAB and choose Simulink and choose blank model to write PID function and to see a PID simulation. And I already finished it, so I will show you a finished one. Here it is. All the blocks I placed on blank model are choosing from here, block Simulink. And this is the menu of block Simulink you can choose for your work. Before start PID, let's see the system, the basic one, which is closed loop system. The closed loop control or closed loop system will look like this. Here, this is closed loop system. And it can control system in a certain level because it has a feedback. When system has a feedback, it means system do not use input to drive system directly, unlike open loop system. Here is open loop. Open loop do not have a feedback line, but closed loop we have a feedback line. Closed loop we use a difference from input and output to drive system, which is an error. When system working on it, the output will be increased, which means a decreasing error. So closed loop is a convergent loop. Here, let's see the graph. Look how it is. Okay, here is the graph of closed loop system. You can see that the graph is really look like a unit step function, which is the input that we added in. Okay, maybe you cannot see it clearly. So I will show you a unit step function in the graph. Okay, run the model. Okay, here the blue line is a unit step function, while the yellow line is an output. From the observation, there are some error appear here between these two lines, which means the system cannot respond in the effective way, but still convergent system. Okay, let's discuss with the graph. As I have said, the error is the one that drives system, while the output will be increased when compared with input. It will give error to drive system. So The more output increase, the more error decrease. In some certain point, it finally steady with some certain error. That called steady state. So the error is an important parameter. So PD control will have an important part which can change or adjust an error before it's going to drive the system and make a desired response. And the first part of PID control is P control. It will improve an error value by gain an error value. Okay, I will change I and D control in 0 value. Just click it and change to 0. Okay, P control is again the error. And then the second one is I control, which is integration, and it also had a gain of integration called Ki. And then the last one is D control or derivative control. And it also has a gain of derivative called Kd. Let's go into a detail of PID control, beginning with P control. It is actually gain that multiply error to have a higher value before drive system. So the system, after receive the error that multiply gain, it will respond faster. If I define one as a gain of P control or Kp and others are 0, it's actually a closed loop. I will run this model to show you a graph. Here, the blue graph is an error. You can see the label above. It's shown that the blue graph is error, and the yellow graph is output, and the orange is input, which is unit step function. You can see that output is the same as closed loop response, but if I increase Kp, increase it to 10, see? The error which drive system has a high value at the first second, very high at the first second, but rapidly decrease in the following time, while response rapidly increase and oscillate before going into a steady state. So we can conclude that P control serves to accelerate the system and make system respond faster. But disadvantage of it is the occurrence of overshoot and oscillation. If you want to see a clear picture, I will increase Kp more than 10. The rise time now is only around 2 or 1, and if I increase this to 50, see, the system gone faster. But you can see a higher oscillation and overshoot. This is the first part of PID control. So it can conclude that PID control has a strong point, which is making a faster system response and decrease steady-state error, but the weak point is the occurrence of overshoot and oscillation. Next, decontrol, which is the block below here. Decontrol is dip or a derivative of error which ran into a decontrol block. It is multiplied by D gain or KD and then find a derivative value before combining with a PID control value. You can notice that dip is a slope of error. As you can see here, the blue line is error. Oh, I will change KP back to 10 to make a graph look easier. Okay. If you notice on the blue line or the blue graph, you can see the slope. The slope of the blue graph has a negative value. It will has a negative value until it reach a turning point. Yeah, this is the turning point. When it reaches a turning point, the slope will change to the positive value. Okay, I will show you how it works with the error. At the time where slope has a negative value, until the turning point, if use those negative value by combining with a value from PID control, it will make a reduction of PID control. So it means that the control will delay the system. But at the turning point, when the error reaches the turning point, the slope will change to a positive value. And the value of PID control or response will change to a negative value. But the blue graph has a slope which is a positive value. So it's going to reduction to each other. So decontrol can delay the system every point of time and it will end its role when slope turn to zero, which means the system is in a steady state. Okay, I will adjust KD to show you the graph. Choose 2. The way its delay system is decreasing overshoot and oscillation. From KD you can see the graph has changed a lot. Okay, I will add more value around 10. The previous graph has a bit overshoot, but now it's overdamped. And the another point that can tell that this is a delaying system is rise time. Rise time at the first steady state point was increased to 7 seconds, which means system works slower, but setting time is lower. Ah, I will go back to show you what the setting time is. Setting time is a time when systems start until it go to a steady state. Here, setting time is around 6, but when we add the control, the setting time will go lower. See, the rise time will go higher. Rise time is increased to 3 seconds, and the setting time is nearly 3 seconds either. It's nearly equal. So the strong point of the control is increasing stability by the vanishing oscillation and overshoot, but it makes system be more slower. Next is eye control. Eye control represents integration. As you know, integration is the area below the graph at every point of time. So it means this part will collect our area below the area graph and then combine it with value from P control and D control. Notice that at the first point, the area has the highest value and then slowly decrease at the end. And every time when the feedback went back from the output, this eye control part will collect the area below the area graph, but this area has a high value at the beginning, and this area will go lower according to time. So it means that the value from eye control will rapidly increase in the beginning and slowly increase at the end. When it combined with P and eye control part, it will increase, which means eye control will serve to accelerate the system, but the rate of acceleration will decrease until it will be zero, which means in steady state. Okay, I will add some value of Ki. Have you seen the graph which is sliding up? Okay, let's see the graph when I extend time range. See, the graph is going to steady state because at the point Kp and Kd already balanced, but there are still some error. Also the area below the graph. So eye control will collect this area value until the graph getting higher to the setting point. Okay, I will change the time range to 100. See, at 100 seconds, it's going to the set point in around 80 seconds. If I give more Ki, see, if the Ki was exaggerated, the oscillation and overshoot will be excess. Okay, I will adjust Ki until the overshoot and oscillation disappear. Okay, there's still some overshoot. There's still a bit overshoot here. Ah, let's do some more. Okay. This is nearly look like a unit step function. Now you can see this is how PID work for the system. Okay, and this is enough for today. The next class we are going to learn how to adjust KP, KI, and KD into method. Okay, thank you everyone.